Hello, everyone. So today, I hope this works now. So when I move, it's perfect. So the plan for today is to talk about graph types, different graph types, and then we're gonna make an introduction to exponential random graph models, which are the basic kind of network models that we use for testing hypotheses. And then we're gonna do a hands-on exercise with a data set on Ottoman revolutionaries in 1896 and 1897. So let's start with graph types. So maybe the most important question that we computational social scientists face is like what fosters connections in social realm. So you can think of various factors like gender or shared hobbies. For example, Akanoja and I wouldn't probably have met if we didn't both share computational social science as a shared area of interest. It could have been that like we would have bumped into each other on a beach or something, but the likelihood is much smaller compared to other things. Or race can be a possible mechanism for fostering connections in the social realm. And given that, I'm going to start by talking about random networks, which are called Erdős-Rényi graphs. So we're going to talk about this graph type because it's the most basic type of graph, the simplest mechanism for tight connection, which is just probability, randomness. Okay, that's why it is called random graph. So Erdős is a very famous mathematician, actually. And he's very famous for having authored numerous articles, so much so that like there's something called the Erdős number, right? So if you have Erdős number equals 1, that means you co-authored with Erdős. If you have an Erdős number equals 2, you have co-authored with someone who co-authored with Erdős, and so on. So people actually, measure their Erdős number. So Erdős has a very interesting personality, very eccentric. He's a very prolific writer. So I was told that he would just, I actually read that. He would go on a weekend to visit some mathematician and then stay over the weekend, and they would produce a paper and then moves on. And, it's like me, Hocam, coming over to your place, we would just publish an article and move on. So it's a very interesting personality. Anyway, so he is one of the fathers of this mathematical field. So why do we use Erdős-Rényi graphs? So these are binomial graph models. You will see that it has an exponential formula. And the idea is very simple. So we want to basically start with a graph that has n nodes, n equals 30, 20, or 16, or 6,000, doesn't matter. We just start up with a number of nodes. And we also start with a preset probability P, which can be 0.4, 0.2, 0.5, whatever. Hence, we basically define a random graph, a graph of n nodes, and the probability of connection equals P. There's not going to be a lot of math, it's just for the notation here. So why do we use these graphs, and why are they random? Because each time you basically construct a graph using this formula, G of NP, you're going to end up with a different, constellation of connections. Hence, it is random. So if you have a P, which is the probability of type formation, that is close to 0, then you will have a sparse graph. That means like the probability of, a net forming between a pair of nodes is very small, right? If it grows, then you're going to have a dense graph. Like if it becomes close to 1, it's almost certain that you will have a connection between a pair of nodes, right? So what are some characteristics of random networks, or random networks and graphs? They mean the same thing, but anyways. So they tend to be sparse. they tend to have low clustering coefficients. They don't have a community structure, and it's going to make more sense in a second what this means. And when you start forming the graph, at some point you will see a giant component. I heard that you are familiar with the term components, so a giant block of edges that are interconnected, right? And it suddenly shifts from low connectivity to high connectivity, okay? I'm actually gonna show you a simulation about this. This makes more sense. Are you guys familiar with NetLogo? Ever heard of it? Networks, random graphs. Okay. So this model on NetLogo basically simulates a random graph and the formation of a giant component. It starts with the number of nodes set to 80, but you can vary this to see how, whether the phase transition happens at another time. So when you hit setup, you will have 80 people, as a circle. If you go once, just 2 people will be randomly connected with a probability, set probability. And then you go twice, another randomly chosen pair will be connected. And if you continue doing so, and I'm gonna speed it up a little bit. Suddenly we saw that most people became interconnected. So that's a component, that's called a giant component. And you may be basically skeptical and think that it's just maybe the simulation. And you are actually right to think so, but you will see that even if we start with another random starting point, you will still see a giant component, okay? And still, it's a sudden shift from low connectivity to high connectivity. Let's do it once more. So suddenly, there's a shift, a stark shift in connectivity, okay? So this is basically the idea behind random graphs. So random graphs, again, I want to emphasize the driving force behind type formation is probability and randomness. And are they any useful to understand real networks? That can be discussed because real networks never basically form randomly. There probably is a reason why you actually become best buddies with your, best friends, and you probably went to the same school, or you basically grew up together or something, or you share some common interests or something. So it's never random, right? Like that doesn't happen that way. Moreover, in real life, we would see clusters of people. So small friendship networks, right? Like groups of, for instance, high school students that band together oftentimes. So that's what we understand by community structure. And often we observe homophily. Homophily is a tendency of ties basically doing the same thing based on similarity. For example, let's say Akın Hoca and I both love basketball, and this shared interest precipitates us to go and see basketball matches, and then we become best buddies or something. Or I love cooking. Actually, that's not true, but anyway, so suppose that I love cooking. And then Cihan here loves cooking as well, and we start to cook together. And then we become best buddies. So there's always something that drives that similarity, that drives that connection. And it's called homophily. And today we will basically use this quite a lot. So if real networks are really different than what we understand by, random networks, why do we ever use random networks? So we use random networks because we need to test hypotheses And if the idea is that, for instance, Akın Hoca and I became best buddies because we both like basketball, then the null hypothesis is like having, a shared interest in basketball has no effect on us becoming friends, right? The alternative hypothesis would be basketball plays a role, right? So in order to rule out, reject the null hypothesis, we would like to show that there is some effect realized by shared interest, here basketball. And we will basically show that statistically, across all different configurations of our tie formation, there's a statistically significant difference between random graphs and basically our connection based on homophilia, right? So the idea is very simple. It's like in statistics, you have a null hypothesis. So you say that there's no effect. And the alternative hypothesis is basically you have an effect and you accept the alternative hypothesis if you reject the null hypothesis, right? So we use random graphs in order to rule out certain alternative explanations that basically help us accept our main mechanism behind social connections. So what we observe in real life is usually networks called small worlds. And there's a very famous movie. It's an old one right now. Hold on. Which screen is this? So this movie made this idea very popular. We don't have sound.
Do we need sound?
I mean, maybe, but let's not necessarily. Let's see if we can put subtitles. So the story behind this is this guy is a con man, and these are very rich people living in New York, and he basically adopts their way of, life, culture, everything. And he becomes part of them just by saying that he's a friend of their sons, and they simply accept it. And it turns out that they basically didn't have any relation with their son. It's an interesting idea because they popularized this idea of 6 degrees of separation. Have you guys heard of it? Like the idea that any two people in the world would be connected by 6 degrees. And that's an amazing idea if you think about it. Like me and Trump will have approximately 6 connections, something like that. And this movie popularized this idea. If you're interested, and you can definitely check in. But this basically idea comes from a very famous experiment conducted by Travers and Milgram. Maybe you might have heard of Milgram because he's very famous with this prison experiment. And he's the main reason why we have not IRS, what was it? IRB today.
Yes.
All these ethical reports and such things that basically are a pain in the ass. Anyway, so these guys conducted the following experiment. So they decided that they're gonna actually give an address, a name of a stockbroker in Boston to random people. Imagine someone who lives in, I don't know, Chicago or something, or some rural area in, I don't know, Texas or something. And they say, here's the address and names on John Doe, and he lives in Boston. Could you please forward this letter to that person? So that person has no idea who John Doe is, who that stockbroker is. And what does he do? So does this letter ever reach to that stockbroker? So that's the experiment. And what really happens is, so I'm, for instance, some farmer in Arizona, and I received this letter. So I don't know the stockbroker person. So I forward the letter to the sheriff of the town because he's better connected. So I give it, so connection 1. And the sheriff thinks I don't know the stockbroker person. So what do? I forward this letter to, I don't know, some other sheriff in some neighboring town because he has better connections, more connections than I do. And he does so. And that new sheriff has, okay, I have a cousin who lives in Boston. Maybe I'm going to forward that letter to the cousin. And then the letter goes to the cousin. And the cousin somehow has a friend who knows people, you know, you get the idea. So everybody forwards the letter to someone who they think to be better connected to them themselves. And in the end, they find that 20% of the letters reach the destination, which is quite remarkable considering that it's 60s and still today US Postal Service isn't great, but like it reached. And you may imagine that a lot of people actually didn't even care, you know, like a lot of people might have stopped the experiment or something, but the interesting finding is that the average path length is 6.5. I think that's an amazing finding. So just 2 random people chosen in the United States can be linked through 6 paths on average. That's a remarkable finding that has, fostered this idea of 6 degrees of separation. And this experiment has been reproduced recently, considering, the online age now. And it turns out that given the intricacies of internet connection, this path length is even shorter than 6, okay? So, I thought I had a, let me show you how a small world network looks like. So you're gonna see that it's pretty different. You start with a similar layout, some bunch of people gathered around a circle. We have a rewiring probability, so it's 0.3. We can change it. So when we hit once, then like we're gonna have random connections. I'm going to fast forward. And what is interesting here is you will see that not everybody is connected to everyone else, okay? But it is possible for everyone on this graph to reach some other person on the graph, okay? So it's not disconnected. It has small local communities, which is the most important. Maybe if you were able to show change the layout, that would be better, but it doesn't let us do that. Let's highlight to, that doesn't do anything. So when you simulate, you find some other constellation of connections. For instance, this person seems to be better connected than others. This person is not connected, but there seems to be still not many people with high degrees, that is many number of connections, but it is still possible to navigate from one part of the network to the rest, okay? And next we have the scale-free graphs. And it will make it more obvious for you the difference behind the mechanisms of connection. So scale-free networks have a degree distribution that resembles a power law distribution. So does anyone know what power law distribution is? Engineers in the classroom?
Power law distribution.
Yeah.
It's a distribution that usually we can map it to a linear thing that it's the power of the probability side, and then we move to the on the end, it comes down, and we can map it to the real world things like, let's say, earthquakes. Map it with other earthquakes, and we have, let's say, lots of small earthquakes, but we have usually the number of districts with a high magnitude was very small. Yeah, that's the.
Yep, that's correct. So power law distribution looks something like this. It has a very long tail. Okay, it has a longer tail than a log or chi-square graph. And here, just to actually give you a sense, they put here a normal distribution. So when you actually log it, it's going to give you a linear line. What is interesting here, there are lots of observations over here that have, you know, small values, whatever that values are. In our case, that's the network. So we're going to talk about the number of relationships, but the idea behind the power law is this, like you have lots of observations that have small values and very small ones, few ones that have large values. So the idea is basically popularized through this idea of preferential attachment by Barabasi and Albert. So the more connected you are, the more connections you will receive. So if you are already an Instagram popular celebrity or something, it is much easier for you to have new connections than I do, who probably almost never uses Instagram or social media or something. So the number of nodes with degree k here can be anything, 4, 6, 70 something, is proportional to k to the power of minus gamma, which is a constant. So the idea is, to put simply, there are very few nodes with a very high degree and many nodes with a low degree. Okay. So why is this useful for our purposes? In most social phenomena, actually scale-free graphs are very handful, for example, to model, you know, social and financial networks. It's good for, you know, thinking of how information spreads. You have lots of hubs, a small diameter, but I think showing it would make more sense for you guys. Let me do this. Potential attachments. All right, so notice the progression of connections. So if it's 59 ticks, and we already have lots of nodes that only have one connections, there are certain few, actually there are few nodes that have multiple connections, and these are the hubs. So it gives you a tree-like structure, right? At local parts, let me make this somewhat bigger. And it hasn't helped. All right. Okay. There's a lot of applications in finance, for instance. So investors would like to invest their monies in companies that have already proved successful, right? You don't want to lose. Nobody wants to lose their money. So if a firm is successful, it's proven to be successful, it is more likely to receive high investments than other firms. So if this were a firm, like this would be more likely to receive some investments than this guy over here that has just one connection, okay? You may also like think of this graph as a possible channel whereby we basically model dissemination of information or some disease or something, right? So the hubs occupy an important role. So if you were to disconnect them, then you would basically happen to disconnect the graph, right? But if you were to basically delete this node, that wouldn't make such a change. So when basically people were thinking about how to stop COVID, for instance, they were trying to, you know, intervene to people who have these central positions like hubs. All right, so you've seen that scale-free networks have many hubs, and they have a small diameter, and they have usually short average path lengths compared to others, and small clustering coefficients. because you don't see many triangles, right? Does this idea make sense to you? Have you seen triangles at the local level? For example, okay, let's do this. So suppose there's a person over here, another person over here, and another person over here. Okay. So and let's assume that, oops. I know how to do this. Okay. Suppose you have one person here and another person here and another person here. So these guys are friends. Let's see, A, B, C. Transitivity is this idea that once you have a shared connection, it is much more likely that these people who are not previously connected will be connected. So my friend's friend is my friend kind of behavior. And that basically forms a triangle, right? So that gives us a community structure. That's the simplest form of a community structure. And usually this is the kind of structure that we could observe in social networks. And you've just seen that in scale-free networks, it was more like a tree kind of, branching out to different things. Does that make sense? All right. Do you guys have any questions? So I keep talking, but I want to make sure that I'm not talking by myself.
Been waiting for a calling.
All right, excellent. Let's hit exponential random graph models then. So once more, why did we basically talk about random graphs? We want to test hypotheses. And when we're basically studying social phenomena, the mechanisms behind social connections, usually something like homophily or transitivity, like you're friends with someone, or you meet the love of your life because you have a shared connection or something, or you become best buddies with a person because you have similar interests, or you went to the same high school or something. So there's always some mechanisms, that a process that both of you went together, right? So again, in order to demonstrate the effect of this shared mechanisms, we want to basically rule out that this connection is random. Hence why we're going to basically use random graphs in order to test hypotheses. So what does it mean to model a network? It basically means that we're going to construct a probability distribution that accurately approximates the network, okay? And exponential random graph models basically construct this probability distribution, and they're trying to approximate the network to the observed network. So before we get into the details of these forms of models, let us think about what can we study with this family of models. So basically we can ask two kinds of questions. Some things that focus on covariates. For instance, do legislators in the same political party collaborate more frequently than those in opposite parties? A fair question, which has been studied many times. You can see various published papers that basically cover this, especially in American politics and political science. Or do states with democratic governments have more alliances than those with autocratic regimes? So, for instance, this question is a good one to test this democratic peace theory, right? So, which suggests that democratic governments don't go to war with one another. So that's one way of basically studying this, right? Here we're basically looking at whether similarities drive certain outcomes. In the second type of questions, we're focusing on interdependencies. Let's see, are two states at war with the same third state less likely to be at war with each other? So this question builds on this idea of transitivity, which I just showed you. So you share a common connection. What is it? What is the likelihood of these two previously disconnected states to go to war with one another? And tie formation representing going to war with one another. Does that make sense? And nodes are states. Or are there popularity effects in the choice of co-authors? So do I co-author with anyone, or do I basically try to co-author with people like Erdős, which will also bump up my popularity, right? So I'm going to, for instance, test the effect of degrees, number of connections that my co-authors have. So
first question is to
okay.
The interdependence, but
I want to draw this so badly. Okay. All right. So this whole idea is grounded on this assumption that network analysis is based on interdependencies. And this is a major difference between, statistical techniques like regression and network analysis. In statistics, everything must be independent, like independent observation. Here, like you're working with relational data. I'm saying this because, like, if this is a network, okay, just keep making connections over here, something like that. So something that happens to A, by definition, will have impacts on the rest of the graph. And the deletion of this edge will have consequences for the rest of the graph. So you cannot assume that just because you're, changing one side, these people or these ties will not be impacted. So all these interdependencies, like variables regarding interdependencies, involve these interconnections. For example, triangles. Popularity here is the idea that like you receive a lot of, oops, I'm still erasing, hold on. Suppose you're this A, okay? Popularity is the fact that you're popular and receiving a lot of incoming ties on a directed network. So this is popularity. And for the counterpart idea is sociality or something, yeah. And this is like sending lots of ties to others. Why is this interdependency? It is interdependency. Basically, you are forming a tie by sending it or receiving it, which is going to change the rest of the structure of the network. Okay. Let's think about implementations of this idea. For instance, like if all of your friends are smoking, you become more likely to smoke. Or if like this is a published paper, by the way. So James Moody is a sociologist at Duke University, and he published this paper on high school friendship networks. And he finds that, empirically speaking, most friendships follow race. So whites hang out with other white people, white students. Black students hang out mostly with other Black students hang out mostly with Black students, and so on. Okay. And the moment you actually try to, befriend another race, okay, like there's all this social pressure or acceptance or unacceptance, whatever you call it, will come with it. So the formation or deletion of an edge has implications on the rest of the graph. That's why. Okay. Any other questions? Okay. All right, so how do we do estimations with exponential random graphs? So basically, it's a probabilistic modeling where we use the likelihood framework of inference. Have you guys heard of maximum likelihood in statistics? So what's the idea behind maximum likelihood, roughly?
We have some and they have their own focus to value, and we maximize give us the parameter value that applies to actual parameter value.
Yeah, exactly. So we're going to use the same approach. There will be two algorithms that we will be using depending on the structure of the equation we built. So just maximum likelihood or Monte Carlo Markov chains, which are called MCMC. If you've ever been exposed to the most fun version of statistics, and I said this very sarcastically, Bayesian statistics, you will see lots of, Markov chains. Anyways, so what is this idea? We're gonna run a model, an equation like any regression equation, y equals, a plus b1 x1 plus b2 x2 plus some error term, right? So these equations, when you will actually run them in R in an hour or something, will look the same. But how do we basically estimate these b1 and b2? So one way to do this is to use maximum likelihood. If you have only, covariates that build on homophily or something, if you have an interdependence term like triangles or something, then you will be using Monte Carlo Markov chains. Does anyone know what a Monte Carlo Markov chain is? Or can? No? Yes?
Basically, the Markov chain, statistical decision that we are making. And as I am not sure about this development, but the next choice that you're going to, the next decision that you're going to make is dependent on the current situation.
That's Markov property. Yes. So why is it Markov? Because the idea is that what you do right now at time t will have implications for t plus 1. But when you're actually at t plus 1, t minus 1 will have no impact on the step. So only the present step on the future step. It doesn't record the past. Okay. And it is useful for the following reason. Exponential random graphs, as you will see in a second, look like this, horribly complicated. Okay, these are exponential models. And when you include interdependency terms like triangles or something, that it becomes even more complicated to estimate. So they're running this algorithm called Monte Carlo Markov chains in order to approximate the probability distribution. So the idea is that, so you start at a random point here, and then you run the algorithm. So there's another network configuration, right? So is it more likely to happen this one than this next one? Is it more likely to happen than this one? If yes, then ditch this. You actually accept this one, and then you move on. You simulate something else. Is this one more likely to happen than this one? No, okay, ditch this, make another simulation. Is it more likely to happen than this one? If yes, ditch this. Do you see the idea? So every time you're trying to basically make the parameters that are most closest more likely to happen. And when you actually run this algorithm enough, it produces a chain and it converges to a certain set of parameters. It is similar to this idea of maximum likelihood, and you will see how it happens in a second. So these are parametric probabilistic models, and the idea is that we observe some X, in our case, that is a network, Okay, for example, a friendship network at some US high school, which is a draw from a random variable, X. If we are modeling a high school friendship network in the US, then this large family of random variables would be high school friendships, right? And one instance of it would be the small x. So it's a function of what? X and theta. X is the random variable and theta is the probability distribution. This is just a general framework for basically most of likelihood framework of inference. And we're trying to maximize these values that basically validate the model. But it could be an adjacency matrix, which is the structure of a network. It can be some text in a document, or it can be some dependent variable in a regression model. So exponential random graphs look like this, and it is less daunting than it looks. So this is the probability of a network with a certain, family of effects that are of interest to our purposes. For instance, if we are studying, again, a high school friendship network in the US, let's say one possible hypothesis is that friendships are, driven by race, right? So theta would have this race parameter, right? So we're trying to estimate whether being of the same race would make people more likely to befriend one another. Could be being at the same grade. So 10th graders would be more likely to befriend other 10th graders and so on. Or maybe gender, maybe girls prefer to, be friends with other girls, and the same for boys. We don't know. There might be some different explanations for friendship. So this is your network, okay, observed network, which can be expressed in this exponential format where this is the theta, like all these effects that we just talked about, but estimation, hence this tilde thing. And these are basically the weights. And the denominator is the normalized. What does that mean? So the whole idea behind exponential random graphs is that you're going to basically simulate a bunch of graphs that have these properties that you're interested in studying, like race or number of degrees, number of triangles, something like that, okay? And given all these possible configurations, like you have the universe of probabilities, how likely am I to observe the graph that I am studying empirically in this universe of possibilities? Does this make sense? So I look at all possible configurations, and how likely is it that I basically have a network that I'm studying over here? That's the idea behind ERGMs. They treat a network as a single observation, hence this idea that, X is a draw from a random variable. So this is your network, which is drawn from a set of networks, random networks, and you're calculating the probability of seeing networks resembling to the one we study. Okay. Shall I explain this again? Does this make sense? So to put this simply, suppose I have 3 outfits, right? Like 3 skirts and 3 tops. So I can have how many configurations? How did you arrive at that conclusion? Okay, so you can do all possible combinations, right? So imagine that you observe me with a green top and some blue skirt. That's one possible outfit out of the entire possibility of outfits, right? 1/9, right? This is the exact same idea. So you have some network, for instance, a friendship network where you observe 20 people. And they have some attributes like gender, grade. So what are the possible combinations, network combinations, referring to how many different friendship ties would happen, different friendship ties, given this distribution of, grade and gender or race, whatever you actually choose, out of the entire possibility of tie formation. So is it more likely or is it not likely? Okay, does this make sense?
I'm not getting so maybe you can clear it up. But all the possibilities isn't always going to look at so much.
Yeah, that's why we are using Monte Carlo Markov chains. So you're not going to be able to basically simulate all of these, but
Like 9 different combinations, but you pick one of them. So always going to look like a very unlikely thing to happen. Like it was random because of one.
Maybe I shouldn't have given that example. I just only gave that example to give you a sense of this ratio. But of course, it doesn't translate it into the network realm. So because in the network realm, we're working with relational data, right? So for instance, in this classroom, imagine all the possible pairwise tie formations. There can be many. Actually, let's do this. That will make more sense.
Just something like that. You run simulation here, and 10 out of 9 times, I'm from Japan, and then you actually become. So you say it's just by chance. So it's not significant.
Like imagine that we are looking at a small network, and these would be connections. Akın, Başak, Cihan, something. Cihan, another Cihan, and Cihan, Ayşe. 2 Cihan doesn't make sense. Anyways, let's go with this. So how many nodes do we have? Akın, Başak, Cihan 1, Cihan 2, and Ayşe. So my hypothesis is that like people, for instance, who are of the same gender are more likely to befriend one another, supposing that we know the genders. Okay. So if the gender hypothesis is true, what would be all the possible connections that we would observe? Like if that is true, we shouldn't be likely to observe this, right? Like, but and the same applies to this one, or the same applies to this one. Only this might be possible, and we would also observe Cihan 1 and Akın, Cihan 2 and Akın, right? Something like that. So in one configuration, you would have all these Akın, Cihan 1, Akın, Cihan 2, Cihan 1, Cihan 2 kind of thing. In another configuration, you wouldn't have any of these. So you basically simulate all possible outcomes given this mechanism of race, and you compare it to the observed network, which is this. And how likely is it for me to observe this network compared to some random network configurations? That's what the ratio gives you. And maybe it's not statistically significant, this race, given this data. Okay, does that make sense now? Okay. All right. So the most important thing to remember when using ERGMs is to specify. It looks very straightforward, but it isn't usual because a lot of people make these mistakes, to thoroughly define what edges and nodes are. Nodes are usually straightforward, but edges are not. And James Kitts recently wrote a piece about this, and he was saying a bunch of famous scholars basically conducted a study on Facebook, using Facebook data, I mean, looking at friendships. So what is an indicator of friendships? Like 2 Facebook connections sending each other some text, right? Through this mail thing. It's been a long time since I've used Facebook. I don't even remember, I think messaging is the word. So when you send a message, it would be something like a picture or some intimate text or just hi, something like that. So they consider all of these indicators as, evidence of friendship. But if you think about it, it doesn't make sense, right? Why it doesn't make sense? Because like, it could be that I'm best buddies with, let's say, Cihan over here, and we don't bother to talk about, through Facebook. So we just call. So here, the gist of the thing is, like, the absence of a tie should be clear. When you're theorizing what an edge is, you should also theorize what an edge is not. And like, the strength of friendship may be potentially, studied with the kinds of, media tools that you're sharing with the other person through messages. But just because you're sending cute cat pictures to some other person doesn't mean that you are best buddies with that person. You are best buddies probably if you're talking about your intimate life or something, but not sharing dog or cat pictures. So it is very important for us to specify what an edge is, especially in the in social sciences, because it's somewhat more straightforward. In engineering, it's usually construction sites, websites, or something. Connections are more tangible things, but when it comes to social phenomena, it is less so. So we want to define what edges are and what kind of interdependencies or dependencies we will have, like transitivity or reciprocity. So if I send a tie to someone, will I be able to receive the tie back? Imagine this as a trade network. So I don't know, sell socks to Iran, some Iranian company. Will the Iranian company send something back to me, or is it just one way? Or I'm France and I'm borrowing from Spain. Will Spain also borrow from me? These are all, published papers. So reciprocity, the idea of reciprocity in a directed graph. So you want to specify what all these things is. Like on a trade network, it's very straightforward. You have states that are represented by nodes, and edges represent, like here, money flows, right? So who is borrowing from another person. And then given, like, once you specify all these things, then you're going to use your software. In our case, it will be R, and use maximum likelihood estimation, or MCMC, to find the most likely set of parameters. Okay. So the interpretation of coefficients are a little tricky, but I'm not going to get into all of the details. So at the basic level, it is similar to what you would see in a regression case. So you observe an output, and just, in all regression outputs, you will have stars or no stars. Stars signifying you have some statistical significance at some level, 1 star, 2 star, 3 stars, whatever. And given that you have some statistical significance, you're going to look at whether the statistic is positive or negative. And a higher statistics will be that you're seeing more tie formation that can be explained by that statistic. For instance, if you were to run something like this, here's the texting. Suppose you have a network model that looks like this. My network, let's say high school network equals edges plus race and gender. So these will all have parameters, right? Some beta 1, beta 2, and R will give you an output of this. So suppose you have this. Beta 1 that is positive and statistically significant, something like that. So what does it tell me? This coefficient for race is statistically significant and it is positive. It means that I see more tie formation between nodes that have the same race than if, you know, they were of different race. Right? Race makes sense in explaining friendships, how friendships form in this high school, for instance. If I see beta 2 statistically significant and negative, this would mean that I see less tie formation, friendship formation between people who have the same gender than if they were of different genders, which means that people have tendency to befriend people from other sex, if this coefficient were true. If we were to find the reverse, then we would see more tie formation between people who are of the same gender. Okay, does that make sense? Basically, the interpretation at this level is very straightforward, but don't forget that this is an exponential family of models. And if you have been exposed to logistic regression, you will know that the interpretation of, you know, one unit change in something is not that straightforward, because what you're actually modeling is log odds of ties, which is not probability. So you have to transform this. Okay. So what can H be? Like this effect that we are modeling can be a dyadic covariate, like being democracies, being autocracy, if you're modeling some interstate relationship, or sender covariate, for example, borrowing, you know, where, lending from the other way. Lending money, if you're a state to another state, would be a sender covariate. Receiver covariate would be something like, you know, just borrowing. The reverse. Reciprocity, we just talked about it. So I send a tie and the other person sends the tie back to me, right? And it can be popularity, sociality, and transitivity. So again, popularity is the fact that you're receiving lots of incoming ties. A lot of people love you and they want to connect you. Or you're very social, you basically want to befriend everyone, you're sending ties to everyone. Or transitivity is this idea that, like, I'm more likely to befriend a friend of my friend. Okay. So if we were to represent it, this would give us a triangle. I guess I'm going to actually leave it over here because I want to talk about the diagnostics and the rest when we have the output, because it will make more sense to talk about how relevant the results are when we have the results, if that makes sense. But if you have...
Some participants don't have a background in modeling this advanced.
Oh.
So that is one of the reasons why some of them may not be able to, because in the morning, they basically took network analysis from an engineer, basically built like a computer engineer.
Okay.
I don't think they had like causal inference difference regression discontinuity from Serkan Güzel as well. But this modeling is, I don't want to speak on behalf of you, but it's too advanced based on what we have been doing. Okay. So this is being recorded anyway, so this is something that they will probably be returning several times over the next months. So I would say, like, let's go ahead with this because this is very valuable for me as well. But the reason why, you know, you're not getting too many engagements is that this is a little bit difficult. Okay, okay. Then maybe I should have done intermediate. Translate.
No, it's okay. Like I didn't know, so I would have actually talked about, you know, communities, blogs and stuff before doing this community detection.
This is the kind of level that will get you into good journals as well. So I don't want to say that, oh, let's continue like easy, because I think you can like connect, you know, build an easier foundation by yourself as well. But this level of detail is what is going to get you into good journals. So I would say let's go ahead with this.
Okay. All right, I can also briefly talk about community detection if like,
I mean.
when we
everything
do-
Has your plans.
all right, at this point, I think I'm gonna stop lecturing here and then we're gonna resume at with this hands-on exercises because I think it makes more sense for us to see how things happen than talk theoretically, because if people haven't been exposed to logistic regression, it's hard for me to explain the interpretation of coefficients.
They had a refresher and introduction on regression OLS from SICSS, which is a system. Then they had a definitive and regression discontinuity from SICSS as well. But you know, these things cannot be learned in 2 days.
Yeah,
At the end of the day, I mean, the pathway to arrive at this point will be several months, if not years. So my suggestion would be, I would say, complete this as
Okay.
you would normally would, because I'm really interested in the other slides as well. Like, do it for me.
okay. So before we continue, actually, I put some references over here. So these are the best two, both of them are books on this. This one is more recent, and this guy would be my former advisor, and he's a guru on network analysis. And they basically explain the statistics behind it. But if you're not necessarily interested in that part, they also talk, you know, about the application part with, you know, concrete exercises. So it's very useful. This one is also like this, and it doesn't only talk about you know, applications in political science. It gives you several examples of from sociology and something else. So these books are very handy, and I'll be sharing my slides with you. So anyways, a network model would look something like that, plus some more maybe dependency terms. Beta 3, like transitivity. Okay. So you will observe an output just like you have in a regression table. So you have the formula over here in R, and you have the first coefficient and you know all these standard errors and estimates and stars, and the second one and the third one, etc. And you'll see in a bit how it looks like. So the problem with this kind of models is that you cannot talk about 1 unit increase as you would have in OLS regression. OLS regression, I love it because it's really straightforward. We can say something like 1 unit increase in age gives us, you know, this unit increases in wage or something. That's beautiful because like that's very straightforward. That's not what happens when you're working with nonlinear models. So this is an example of a nonlinear model, as you know, evidenced by this beautiful equation, which has the exponential format. So when we try to basically make a 1 unit increase, what it would mean is like we're going to put someone over here. So the problem is that's an exponential thing, right? Like some of you actually do the math better than I do. So 1 unit increase, if you want to look at the difference or 1 unit increase, you have this expression +1 minus exponential something, the same thing. And how would you calculate the difference between two exponential things? The short of the answer is, without skipping the math, instead of linear ratio like that, because it's multiplicative, right? Exponential. So 1 unit increase would be something like this one +1. Plus the same thing over here, and then when you actually do the algebra and cancel everything out, you would have the effect for 1 unit increase. Bad news is we would have been done if you were in Logit, but this is somewhat more complicated because network analysis suggests that each phi doesn't have necessarily the same weight, right? So if you're making a change in anything in one edge level, the result isn't necessarily the same across all edges. So you're gonna find some result, for example, an extra tie formation, but holding everything else constant. But if you modify something else, then you would have to add another coefficient and multiply it basically. And what is interesting is that because it's a nonlinear model, for instance, the probability of having one tie plus one tie isn't the same, isn't linearly growing, you know, so if you wanted to have two additional ties, like that wouldn't fall on a nice linear pattern. And the way we actually compute the effect of, you know, each coefficient is by using the inverse logit function, 1/1 plus exponential minus x, the effect you're trying to find. And that's going to give you the real effect. But everything you see in this model as output, like coefficients will come as a power of an exponential function, right? So it's going to be e to the power of the coefficient. Let's say 2, e to the power of 2, okay? So that's the log odds, because we are working within the realm of exponential graphs. So in order to talk about probability, you have to basically use the inverse logit function. Fortunately, people using R did a nice function to, you know, convert this easily for us without you requiring to do this computation, but it's not that complicated. It's 1/1 plus exponential minus x. Anyways, this is going to give you the effect of, you know, whatever you're looking at, let's say transitivity, on tie formation. Tie formation, again, might represent anything, traits between states, or friendship among people, or I don't know, like marriage links. There's a very famous study, maybe you've heard about this Florentine networks. Paget is a very famous network analyst at U Chicago, and he wrote this basically pioneering paper on the Medicis and explaining the rise of the Medicis to power. So the question is very straightforward. The Medicis were one of the most powerful families in Middle Ages, but they were not the wealthiest in their times. They were not the noblest or something, whatever that means. They didn't have any particular social capital that would basically help us to predict them as, you know, like the emerging power of the century. But they became anyway. How was it possible for them to obtain so much power? And the explanation he gives us is, look at these marriages, intermarriages between families of Florence, important families of Florence. And his argument is they rose to power because they strategically married important families, so much so that, like, any transaction between any two people would require going through the Medicis. So they had this brokerage power. They mediated everything. They knew the information. They never directly controlled power, but they did everything through behind the curtains because they had all these links. Wait, why did I actually talk about this? I forgot. Look.
Explaining something about the exponents. I was too busy finding that article and sending it to other people that I also.
Oh yeah, I'm sorry. I completely forgot. The data set is available. It's we can also look at this. So you can basically use ERGMs to simulate this network. Why did I really talk about this? I completely forgot. I'm sorry.
I'm just like sending them material related to this via chat as well.
Yeah. Okay, let's go back to the technicalities of ERGMs. So ERGMs are wonderful. I love them. You're gonna love them as you actually work with, play around with them. One vulnerability they have is this problem we call degeneracy. So degeneracy is a measure of the sparsity of graphs. So when you're simulating graphs in your MCMC algorithm, if you bump into degeneracy problem, what you have is either a lot of a lot of empty networks and full networks. So there are lots of observations that are on either sides of the spectrum. You know, tie equals 0, number of ties equals 0, number of ties equals the maximum number of ties that could possibly happen. And very few observations in between. So that's a problem because that makes your coefficients unstable. So if you're working with ERGM exponential random graph models, this is one thing that you should bear in mind because they are very prone to degeneracy. And again, degeneracy is a measure of the sparsity of the graph. So instead of finding the kind of configurations that you want to find in the observed network, you either have a full network or a completely empty network. You are basically pulled to either of the extremes. And that's going to give you an unrealistic characterization of the data generating process. So how would you combat degeneracy? And we will talk about this. One thing is to basically play around with the parameters of this MCMC algorithm. So you want to basically elongate the chains and burn in. That's one way of doing things. But also, more importantly, I think it's like the remedy is one that is theoretical. So is the network or like all these data that's you're attributing to your nodes like gender or age or whatever you're basically attributing have any multicollinearity problem among them. So multicollinearity badly affects, for instance, ERGMs. The other thing is some of the interdependent structures like triangles are very prone to degeneracy. For example, if you're looking at the effect of degree, this is called a 2-star. Why a 2-star? It has 2 edges and the star is 5. You can have 3, 4 up to K. Anyways, so if you want to look at the effect of 2-star, either you will find no star, 3 people over there, or this, which will be complete triangle. And triangles are also very prone to degeneracy. So basically, in a complex network which has zillion different connections like this, the triangle or this kind of configuration is one of the most observed ones that you will possibly find. And if you just put a 2-star, you will have degeneracy because you're overcounting, you're basically inflating all the coefficients, you're going to have a degeneracy problem. So in order to take this under control, what we would be using is, using some penalty coefficients, like instead of, for instance, using these triangle thing, or we will be using, for instance, what we call GASP, Gaussian Exponential Random Graph something. This fancy word is just like counts triangles as it is, but it assigns them a parameter that down values the effect of every additional triangle so that you're not basically inflating your parameters and basically making your model degenerate. Anyways, I think I will stop here since the study. And I can continue talking about diagnostics during the session.
After dinner, we can have plenty of time. The reason why wait, who was the recording?